So let's take a step back. Remember when we very first started, we kind of talked about energy just a little bit. So what is one thing that we know about energy? Energy must be what? At the end of the day.
It's like matter.
What was that?
It's like matter.
It's like matter. In what regard?
What goes in must come out.
What goes in must come out. Exactly. Okay, so energy has to be conserved. We must maintain energy. So today we're going to be talking a little bit about energy. We're going to talk to you about thermodynamics, specifically entropy, and then we're also going to talk to you about calorimetry and something else. I can't remember. Oh, I guess that's it. Okay, so when we think about energy, we can have multiple forms of energy, right? You guys know some of the forms of energy that you guys encounter on a daily?
Kinetic and potential.
Kinetic and potential, yes, kinetic. And what is kinetic energy?
It's the actual energy, and potential is like stored energy that you could possibly use.
Okay, so potential energy is like that stored energy that we can use. Okay, so that sounds good. What do you mean by the actual energy?
Like the production, or like what's being produced. Kinetic is movement, so I don't.
Okay. So the energy associated with movement, is that what you're going to tell me?
Sure.
Okay, so kinetic energy is the energy that's associated with movement. Okay, so those are two forms of energy that we've encountered. We also have what we call chemical energy. Chemical energy or chemical potential energy are the energy that's stored between bonds. And when those bonds are broken, we can get release of that energy. Okay, so a lot of times when we think about reactions like metabolism, when you're chowing down that food, what happens when you chow down that food?
Your body breaks it down for energy.
Your body breaks it down for energy, right? And so if you guys remember cellular respiration, anybody remember cellular respiration?
Yeah.
C6H12 O6 plus O2 yields CO2 plus H2O. And sugar's the devil, so that's 6, 6, 6. Okay, so this is the chemical for cellular respiration. But we know when we do cellular respiration, we get other products. Those products are 32 ATP, and it's 32 net ATP. Plus heat. So, do you guys have big meals on Thanksgiving?
Yes.
Yep.
Oh, I'm a glutton, right?
Of
we
course.
have cakes, we have turkey, we have ham, we have pies, we have banana pudding, you name it, we have it, right? And I have to fill my plate, right? You know, because you got to taste everything. And so you have a plate that's about this high and everything, and you start chowing down, right? And when you first start chowing down, you're doing, and you have to take that deep breath, right? And you suck in that oxygen, right? And we're sucking in that oxygen because we're going to be breaking down those hydrocarbons or that organic material that we're just shoving in our face. And as you shove it in, you notice you start to sweat a little bit. You know, if you eat really good, right, you're going to sweat. Because if you're not sweating, you're not eating good, right? So you'll notice that heat come out, right? So that's part of the process, right? Because as you're breaking down those hydrocarbons, you're starting to produce some of that heat, in addition to that ATP that you're going to be using later on in the cell. Okay, so pay attention next time, be a glutton, Eat all that food. Don't blame Dr. Henry if you eat too much and get a little sick. But pay attention. See if you get a little hot. See if you sweat a little bit. Okay, so that process generates heat as part of the equation. So you're getting heat being released in a situation. So if heat is released, is that endothermic or exothermic?
Exo?
Exo, that's correct. So if heat is being released from a reaction, it's exothermic. So us grubbing down on Thanksgiving dinner is an exothermic reaction. Make sense?
Yeah.
Oh, we got 12 people here now. Ooh, we're really doing it today. Okay, so let's say we're barbecuing, okay, on the grill. We put our charcoals in there and we get them all lit up. So us burning those charcoals to grill our food, what type of reaction is that?
Exothermic.
It's also an exothermic reaction.
Oh.
Right? And specifically, it's a combustion reaction, right? Just like
That's what I was gonna say.
just
Combustion.
like a metabolism, it is a combustion reaction, right? And so in that context too, we're breaking down those hydrocarbons, okay? And in all of those situations, heat is being released. And often we'll be releasing heat again when we're producing raw materials, like if we're making iron from iron ore. So in that context too, we're putting it in that situation, we're actually putting in heat to allow that conversion to happen. Because if without the heat, we wouldn't get that conversion. So if I'm putting heat into the system, what's happening in that situation?
That's endo, right? Because it's breaking the bonds.
That's right. It is endo. So we're putting heat into the reaction. So then that would be an endothermic reaction. Now I want you to sit there and think about this. Okay, so let's say we're burning logs. And we kind of talked about this a little bit earlier. We're burning logs and you're standing next to the log, right? So what's happening in the situation with you standing next to the log on a very cold night?
You're
Or even on a hot
absorbing the
night.
heat.
What was that?
You're like trying to retain or absorb the heat.
So you're absorbing the heat, right? So is that an endothermic reaction or is that an exothermic reaction?
For you or the logs?
For you. That's a very good question. Thank you. You brought me to my next point, Maddie.
Well, I think the logs would be exo.
The logs would be exo, then
So you're endothermic because you're
That's right.
absorbing it.
Yeah,
Yep.
because it's okay.
So yeah, that's correct. Because you're absorbing the heat, it's going to be an endothermic for you, right? But for the log, it's going to be exothermic. So this also brings us to that point. It is relative to what we're talking about. Reaction can be relative. So that means that there's systems involved, right? So for instance, you and the log act as a system. You're taking in heat, the log is exerting heat. Okay, and so together you guys are working as a system. Can you see that?
Mm-hmm.
Okay, good. Okay, so this brings us to our topic of thermochemistry. This is what we're going to be talking about is thermochemistry. We're not going to get to thermodynamics yet, but we will get there. But thermochemistry is basically the study of heat being absorbed and released via chemical reactions or via physical reactions, okay? Or physical changes. Okay, so you guys already answered what energy is. Energy in general is what? Let's see, who's on my list today? Abby, you've been quiet. You haven't had your coffee, huh?
No.
No. So Abby, what is energy?
Isn't it like or provides like chemical changes that provide something to like our daily lives?
Okay, so if we're talking about you living, yeah, I guess that's it. So you would say basically you could say chemical changes, yeah, chemical changes or something that is allowing you to basically do something, right? Because your heart pumping, right?
Yeah.
Does that take energy?
Yeah.
The flying around your food and bothering you, does that take energy?
Yeah.
Yeah.
Yeah. Okay. You vacuuming the floor, does that take energy?
Definitely.
The vacuum
Yeah.
vacuuming the floor, does that take energy?
Yeah.
So basically anything that deals with doing some type of work, because your heart beating is doing work, the vacuuming the floor is doing work, right? So wouldn't that all be energy?
Yes.
Okay. Cool. So let's define energy, basically the capacity to supply heat or to do work. Real general, very, very, very general, right? So if we do it that way, we can sit there and incorporate all forms of energy, right? So we could take the energy that's being accumulated by a dam storing water, or falls falling down the hill, or sorry. So, and as Cassie brought up earlier, we know what potential energy is. Potential energy is that energy that's kind of stored or that is based upon a relative position, like the fact that you have the dam storing that water, and as that water falls, it flows through a generator, and that generator is being pushed through, right? So you're converting that potential energy that's being stored to kinetic energy, right? And then as Kaylin said, energy can only be converted, right? So what you put in, you got to get out. So the way that we get it in and get out is by converting that potential energy to kinetic energy, or that chemical energy to kinetic energy. So let me ask you this. If I have molecules, right? If I have molecules and I heat up those molecules, what happens?
They start moving around quite quickly, don't they?
They
Yeah,
start
they
moving
get
around quite quickly,
excited.
right? So if I have molecules and I freeze them, and I keep freezing them,
Slow.
they slow down, right? So them moving around, would that be kinetic energy?
Yeah.
And them slowing down, that would be reduction of kinetic energy. Yeah, no?
Yeah.
And so that kinetic energy is now, some of the kinetic energy is now being stored as like potential energy. So you're converting those forms of energy. But at the end of the day, we go back to the law of conservation. Maybe. Law of conservation, as Caitlin said, is basically energy can never be created or destroyed. But basically what you put in, you got to get out, right? And what we can do is change its form. Are you guys good with that? Do you accept that? Anybody want to argue? Christian, you want to argue?
No, that makes sense.
That makes
When
sense?
you're talking about changing its form, you're talking about like how it's being used?
Yeah, in a sense, how it's being used. Like, for instance, we talked about chemical energy, right? Chemical energy is a lot of times potential energy. So you're storing energy in the bonds. And when you break those bonds, you're allowing kinetic energy to form, or you're allowing heat to be released. So you're able to sit there and change its form, you know, by breaking those bonds. So you're going from potential to kinetic, or chemical to kinetic.
Okay.
Okay. And then we can also go from chemical to electrical, right? Energy. So we have the ability just to change the form of energy. right? But still, at the end of the day, the energy has to add up. It has to be accounted for, okay? So this is basically just showing you what we just talked about. You know, as we heat up molecules, they move faster, right? You see my little things moving? Are they moving on your screen?
Yeah.
Yeah.
Took me a while to find this little figure, right? And then as as it gets colder, they slow down, right? Which one is going to have more kinetic energy?
Hot.
Hot, 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 right? Just like you on that beach when the sand is really, really hot. You're like, you know, your feet are moving, right, to get to the water. Isn't that correct?
Yep.
I went to Costa Rica for spring break 2 years ago. I can't remember. 2 or 3 years ago. I can't remember now. Old age and everything. And those beaches were hotter than hell. And I like having my feet in the sand and all that stuff, you know. And they were so damn hot. I was just like, nope. Flip-flops the whole time until I got into the water. Okay, so the way that we measure heat is often kind of weird, right? So let's kind of put it in perspective. So often we'll use temperature as a form of calculating heat later on, okay? And I'll talk about this in more detail here in a second. But the way that we sit there and say, okay, yeah, today was a hot day, or yeah, that sand was hot, is by using thermometers, right? And so there's a couple type thermometers, but we're going to talk about mainly two. So one of them is the alcohol thermometer, which is what you guys all have in your kits, and the other one is the biometric thermometers. Have you guys seen a thermostat? Have you opened up, let's say your controller for your AC unit or thing on the wall that controls whether it's hot or cold in your house?
Mhm.
Mine's too fancy, so no,
You never opened it up?
no.
So definitely in the old days. Now they're all using, it's still a biometallic thermometer, but it's used by electrodes, really small electrodes that are doing it rather than these big coil things. If you look at a really old one, so like I have a house in Cleveland that was built in the 1920s. And so I have an old thermostat, one of the first early thermostats, and they really use these coils. And the one that I use, the coil was about this big. The thermostat is about this big. So what happens with the coil is two different metals. And as it gets cold, then the coil actually will shrink. It will actually condense or contract. And then as it heats up, it'll actually expand. So metal will heat up. As metal gets heated, you're going to get expansion of the metal. And as it gets cooled, you're going to get contraction of the metal. So if you guys think about this, think about bridges, right? Bridges in areas like Cleveland, Ohio, and Minnesota had tons and tons of bridges collapse over the years. What do you think most of these bridges are made up of?
Steel and concrete.
Steel and concrete, metals, right? Metals and concrete. So in that context, those metals are contracting and expanding over time. And as they continue to contract and expand and contract and expand and contract and expand, what is that going to do to that metal?
Wear it out.
It's going to wear it out. And so a lot of our bridges, you know, they're due for reconstruction because that contraction and expanding, right? The fact that you're dealing with extreme temperatures like in Minnesota and Wisconsin, that plays a huge part in terms of their infrastructure, right? So the alcohol thermometer. So what do you think is happening there? Or the mercury thermometer? We don't use the mercury one anymore, but in the old days, we used to use the mercury one. What's happening in that situation?
Well, mercury is a metal, right? So it would
Yep.
contract and expand, the same concept.
Not quite. What do we know about mercury at room temperature? Or
That's the liquid state.
it's in a liquid state. So basically from, I think it's a liquid state from 13 degrees to, it might be even smaller than that, but I think it's a little less than 13 degrees, all the way up to, I think 50 degrees, 60 degrees. So,
Wouldn't it be the same concept though?
yep, it would be the same concept, but in this case, you're working with a liquid. So what happens when you heat up a liquid?
If you heat it up, it's going to expand.
It's going to expand also, right? And then some of it, if it's heat up enough, it'll change over to what?
It'll boil.
Steam.
It'll boil,
Yeah.
or it'll go into gas, right? So that concept of it boiling is converting from liquid to gas, okay? So that's the same thing that's happening with the alcohol, okay? Questions, concerns, Cash? Credit? So heat basically is going to be the transfer of thermal energy, right, between two different bodies at different temperatures, okay? And I'll show you an example here so it'll kind of stick with you a little bit. So often we use the term heat transfer or heat flow. So heat transfer is just that movement of heat from one vesicle to the other vesicle. Heat flow is just the movement of heat, right? And does that kind of make sense? So how many of you guys have a boo?
A boo.
A boo, not a
what?
monkey. A
Oh,
boo, not the
I'm like, oh,
monkey,
what?
but you know, somebody you snuggle with in the bed. That's my boo, right?
Yeah, my cat.
I'm sorry, your bae or your cat, yeah. Right? So now either you or your boo, right, are really heavy heat generators. Is that true or not? Or are you guys both equal?
One is.
One is? Okay, so on those cold nights, right, and your cold feet, what do you guys do?
Stick him on his back.
Stick him on his back. That is so mean.
I feel
He-
that, Kathy.
Hey, he generates so much heat, and I'm the like frozen pickle over here. So
I do that
Yep.
to my dad and my boyfriend.
you
They
gotta
both
help
get
me out.
pissed.
So what's happening in that situation where you're putting your cold feet on their back?
Absorbing their back heat.
Heat.
So
Yeah.
you're absorbing the heat from them. And they're getting all that coldness that are coming from your heat, right? So that concept right there, that is heat transfer. So you're transferring heat from him to you, and he's getting all that coldness that's from you going to him, right? So this is going to basically happen, you know, when you first have your two temperatures together, but when you allow them contact over time, you're going to reach a point of equilibrium. So you'll kind of balance each other out. He's going to be real pissed in the beginning because your feet are fucking cold as hell, right? And then you're going to be like, oh, that feels so good. But after a while, you're going to get to a point where you guys meet somewhere in the middle, right? So that somewhere in the middle is going to be thermal equilibrium. It's that point where you meet the same temperature, right? So you and him will be at that same temperature after a while. And usually that's pretty good if you guys are good opposites of each other. If you both have cold feet, then you're both screwed, right? Yeah, no, maybe.
Yes,
He's
you would be.
screwed. I'm still putting my feet on his back.
Okay. So can you guys see it? Can you visualize it?
Yeah.
Okay, so we already talked about endothermic and exothermic. This is just your official slide to say, oh, we've talked about endothermic and exothermic. Endothermic means what? Endothermic, if a reaction is endothermic. Let's see, since you guys are not answering today, tell them we'll call them back later. Jessica. Hey, girl.
I knew you were gonna call on me. I was literally just gonna respond because I knew you were gonna call on me, but it absorbs heat.
It absorbs heat, right? Okay, so if we're taking in heat from the surroundings, that's going to be absorbing it, right? So an example of that is how many of you guys run into walls a lot? Or have exes that throw stuff at you a lot? Anyone?
Well, not
Okay.
X's, but I run into walls.
Run into walls? Okay, so now instead of getting that big old bump, what do? We either get a cold pack. Have you guys worked with cold packs before? Crack it open, and then you put it on your head.
Yeah.
Or the place where you got hit with the cup.
Well, when they're
Right.
not rock hard,
What? Never mind. Yeah, that's true.
because then you need another one.
Yep. So we use those cold packs. Cold packs is an example of an endothermic reaction, right? So in that case, it's absorbing the heat from the outside. So the cold packet actually gets cold. It feels cold. Remember when you guys did that experiment with the, what was it, barium? Was it barium hydroxide and ammonium? No, it was, now I can't remember. Ammonium hydroxide and iodide, I think, barium iodide.
Wasn't it nitrogen triiodide?
No, that was the one that you guys did this weekend. This is the one that you guys did the first set of experiments. Remember where you were
Was it
stirring and stirring and stirring, you got
Yeah,
water
in the
and
little test tube.
yeah.
Oh, yeah.
Yeah. So it was ammonium hydroxide, and I want to say barium iodide or something like that. I can't remember off the top of my head. You guys remember? Sorry. What happened?
Got cold.
It got cold, right? So that's an example. It was actually taking in the heat from the environment. So the tube actually got cold. And when we measured the temperature, it actually started to drop. You guys see that? Or am I just making stuff up?
No, it happened.
It happened. It was real.
Yep.
Okay, so in that situation, we actually showed that we were able to sit there and absorb energy from our surroundings. Okay, so you guys know about combustion reactions. So an oxyacetylene torch, basically we use those to sit there and fuse, we use it now to fuse railroad lines together, or to repair railroad lines, because we're able to sit there and burn through it real simply. Okay, and so that's an example of a combustion reaction. So in that case, you're using acetylene and oxygen, and then these two are doing a combustion reactions, and as a result, you're going to get an oxyacetylene at the end of the day as a product, and carbon dioxide.
So, Dr. Henry, all combustion reactions are going to be exothermic. Is there anything else that's exothermic as well? Or is it
There's tons of stuff that's exothermic. Just
Okay.
combustion reactions are so easy to talk about because everybody's seen fire, right? So you
Okay.
can always relate to it. So that's the reason why we always go to combustion.
It's the most common.
Yeah.
Okay.
Yeah, there are tons. Like when you put neutralization, the heat of neutralization. Heat neutralization, right? You guys did that this weekend. What happened? You went from 23 degrees up to like 28 degrees or something like that, or 27 degrees. Is that true? Or am I making stuff up?
We didn't have a drastic change like that.
You didn't get 27?
Not that I think it. That one was long and horrible for me. If you don't remember,
Are you saying you just blocked it out? You're like, oh my God, it's such a traumatic experience that I just
It
blocked
was.
it all out.
a little PTSD from it.
Your lab's called PTSD.
I was
Okay.
trying to heat stuff that didn't need to be heated, Dr. Henry. Come on.
That's right. I do remember. I forgot to tease you about it earlier. You
Yeah.
beat me to it, Cassie. Yeah.
See?
Okay. So in that situation, right, the fact that you went from 22 is 22.5 degrees if you guys measured the room temperature, And then you went from 22.5 degrees all the way up to 28 degrees. I mean, it's not a whole bunch, but that's something, right? Yes, no, maybe. Okay,
Yeah.
so there, that is an example, right, of an exothermic reaction that wasn't a hydrocarbon, right, or combustion reaction. So there's quite a few that will actually do that. Okay, so let's talk about heat, units of heat. Are you guys with me? Everybody here?
Mm-hmm.
Have you guys heard of
Yes.
calories? Darlene, have you heard of a calorie? Are you there, Darlene?
Yes.
You've heard of a calorie?
Yes.
Where did you hear of a calorie from?
Mm, I'm not sure, but I'm pretty sure I heard about it.
You're pretty sure you heard about it?
Yeah.
Amanda, where do you hear about? You have kids, right, Amanda?
Yes, I do.
So do you count their calories?
I don't count it. I do look at the nutrition facts though. So that's where I hear
Ah.
about it.
So you're telling me in the back of our food, we have calories listed there?
Yes.
So you guys all have heard of calories, right? So when I'm supposedly on a diet, I'm looking at the back of the nutritional fact. I'm like, oh, I shouldn't eat this. Damn, it looks so good, right? Isn't that the way it works?
Yep.
Okay, so we've heard of calories, right? But the calories that we most have heard of is slightly different than what the calories that we use in chemistry. I'll tell you the difference between the two. The calories that you guys are talking about, the nutritional factor calories, that is a capital C calorie, okay? And I want you to remember that capital C, and I'll explain it. It's in the text, but I'll explain it in a little more detail so you guys get a clear distinction between capital C calorie and lowercase c calorie. So for a lowercase c calorie, this is the one that we're talking about in chemistry. And of course, you know this had to come from where? Where do you think, which nation did this come from? The fact that we're using a capital C calorie and a lowercase c calorie.
America.
America, because we got to make things as hard as possible, because if it isn't hard, then it ain't worth doing, right?
Just like pounds
Exactly.
and inches.
Exactly. Yep. Okay, so lowercase c calorie basically is the amount of energy that's required to raise 1 gram of water by a single degree, okay? By 1 degree Celsius or 1 Kelvin, okay? So you're raising water, 1 gram, 1 degree Celsius or Kelvin, okay? So that is the official definition of a calorie, okay? Now, a capital C calorie is 1,000 calories, or we can say it's a kilocalorie, okay? So 1 capital C calorie, which I'll say capital cal, equals 1,000 small c calories. Or I can say 1 capital C cal equals 1 kilocal. So it's important that we distinguish between capital C cal and lowercase c cal. So the stuff you see in your food is a capital C cal. Okay, are you with me? Leslie, are you here?
Yeah, I am.
Good, good. You guys all forget to turn on, you're probably just talking and talking and talking and forget to turn on the mute, unmute yourself, right?
Yeah.
Yeah, I do the same thing all the time. That's why I never mute myself. Plus, I love to talk. Okay, Stefano. So if I have 5 capital C cals, how many lowercase c cals do I have?
Are you asking? I just got here, so I don't know what's going on.
Okay, you need to put on your shock collar. I'm going to be sending it to you in the mail.
Okay.
So So you'll be prepared. Anybody want to help him out? Mauricio, you gonna help him out?
Yeah, I'll help him out. May you repeat the question?
I said if I have 5 capital C
I was
cows.
distracted by my little brother.
So you need a shot caller too, huh? You and your little brother. Okay, if I have
Oh.
5 capital C cows, how many lowercase c cows would that be?
5,000.
5,000. Simple.
Right? Yeah. Cause yeah.
Okay. So it's real simple. We just got to remember capital C cow and lowercase c cow. Okay, so let's see. Let's see how much you guys remember from what I said. Tia, lowercase c cows, what does that mean? Are you there, Tia? Unmute yourself. I guess Tia went to the bathroom. Christian,
Yeah.
what does lowercase c cow mean?
It's the amount of energy required to raise 1 gram of water by 1 degree.
Okay, piece of cake?
Yes.
Okay, excellent. So now let me tell you what the rest of the world uses. The rest of the world basically uses joules. So joules are basically defined, and we use joules too, right? Just depending on the science that we're talking about. Typically in chemistry, we're going to use joules rather than using calories. If you're in food sciences, you're going to use calories, capital C calories. If you're in nutrition, capital C calories. So it really just depends on the area that you're in, okay? Now, a joule is basically defined as the amount of energy used when the force of 1 Newton moves an object 1 meter. Okay, so the force of 1 Newton moving an object 1 meter. Okay, so it was basically a joule was named after Prescott Joule, not Joule as in bling bling Joule, but Joule. Okay, often people will pronounce it joule. Okay, so now the relationship between a calorie and a joule is 1 calorie is going to equal to 4.184 joules. Kayla, I want you to do some math for me. So if I have 1 capital C calorie, how many joules would that be?
1 lowercase calorie. Well, it'd be times 1,000 of those.
Okay. So
So
1
4
capital
point-
C calorie is going to equal to 4.184 kilocalorie.
Yeah.
I mean, sorry, not kilocalorie, kilojoule. Making stuff up here. Or you'll see it written as just kJ. Or we could just say 4,184 joules. Okay, so you guys can do those units, right? Piece of cake? Good, good, good. Okay, so now I'm going to talk, I'm going to talk to you about heat. So we have so heat capacity is basically the amount of heat that is absorbed or released by the change in temperature. Okay, or when you experience a change in temperature. So basically, it's heat divided by change in temperature. So this guy is an extensive property. This basically means that it's going to be dependent on the mass. Okay, so it's going to have mass dependence associated with it. So the smaller pan is going to have a smaller heat capacity than the larger pan. The larger pan is going to have a larger heat capacity. Okay, is that clear? So
Yes.
extensive properties are going to be dependent on mass. Intensive properties are going to be independent of mass. Okay, so let's put this equation to a nice little. So if we say Q equals C delta T, I like to remember that by saying it looks like cat, right? Capital C delta T. And delta represents change in temperature. You guys know what I mean by change in temperature? Yeah? No?
No.
Yes, it's the difference between your initial and your final temperature.
That's right. So our delta T is going to be equal to T final minus T initial. Piece of cake?
Yeah.
Delta T. Don't forget the T. Friday, I was going through brain farts. Not Friday, Thursday. Couldn't remember a thing. Okay, so we also have what we call specific heat. Specific heat capacity. Now that's, again, in this case, we have uppercase C and lowercase c. Again, an American contribution, right? So in the case of the uppercase C, we had capital C. Oops. We had capital C delta T equals Q, right? Or Q equals capital C delta T. So Q represents the heat. Now, in the case of the lowercase c, that represents specific heat capacity. So in this case, this guy isn't dependent on the mass. Even though we have mass in the equation, the reason why it isn't dependent on the mass is because we're removing the mass from the equation. And in this context, we have Q equals M C little c delta T. Okay. Of course, I erased everything except what I wanted to erase. Okay, and again, this is going to be dependent on the mass of what you're working with, right? So here, both of these are iron skillets. And since both of these guys are iron skillets, the specific heat capacity is going to be exactly the same, regardless of whether you have a small one or whether you have a big one. So with heat capacity, it's going to be dependent on size or weight. And then for specific heat capacity, it isn't. So we have a table that of listed specific heat capacities that we could use. And so it's only going to be dependent on the state of the material that we're working with. Is it a solid, is it a liquid, or is it a gas? Okay? Are you with me?
Yeah.
Yeah.
Okay. Okay, so okay, so let me give you an example. So we have water, we have ice, and we have steam. Where is it? Oh, water vapor. Okay, so if you look at the values, so water, the specific heat capacity, or little c, is equal to 1.184 joules per gram Celsius. Does this number look familiar to you?
That's the joule amount. So it's
Yeah.
1 joule.
Yeah, we know that 1 calorie is equal to 4.184 joules, right? So in this context, the specific heat is telling us for 1 gram of water, changing a single degree is going to be equal to this, which if we put into our equation, C, say M delta T equals Q, right? If we put it in 1 gram, 1, we put in this value, 4.184 joules, grams Celsius. And then change that by a change in a single degree. So we put 1 degree Celsius because it's changing by 1 degree. That's going to give us our value. Make sense?
Kind of.
Kind of. Okay. So, but if we look at this, if we go from ice, 2.093, that's going to be the specific heat for that. And if we go to water vapor, 1.864. You guys see that? So they're actually changing depending on the state we're in. Yeah? No?
Mm-hmm.
Okay.
Yes.
Okay, so if a substance is going to be gaining thermal energy, then our T final is going to be greater than our T initial, right? So based upon this equation, delta T is going to be T final minus T initial. So if T final is bigger than T initial, we're going to have a positive value. Make sense?
Yes.
And that also basically means that we're gaining thermal energy. If we're losing thermal energy, our T final is going to be less than our T initial, and our Q is going to be a negative value. Okay, so let's think about Maddie's feet and her husband's or Maddie's boyfriend's feet. I mean back, right?
Yeah, I'm not married yet.
Okay, well, her boyfriend. I'm sorry, I'll correct that.
I was the married one that did that.
Okay. Well, I'm getting Maddie married real soon, right? I approved of the wedding, obviously, so.
December.
December? Okay.
Just kidding.
Okay, that was real quick. Okay, so in this situation, who's going to be gaining thermal energy and who's going to be losing thermal energy? Or are they both going to be gaining thermal energy? Or are they both going to be losing thermal energy?
Can you repeat that, please?
I said, in your situation, in Maddie's situation with her cold feet and her husband's hot back, her boyfriend's hot back. I don't know why I want to keep calling him your husband. Your boyfriend's hot back. So who is gaining thermal energy and who is losing thermal energy?
I'm gaining, boyfriend's losing.
Okay, pretty simple. So that means that there's going to be that give and take within the system, right? So the system is going to either be getting that thermal energy or the reaction is going to be getting or giving that thermal energy or losing that thermal energy. So if the system is gaining, then the reaction must be losing. And if the reaction is losing, then the system must be gaining. Did I say that the same way? Does that make sense?
Yeah.
Stefano,
Yes.
does that make sense?
Sort of getting there.
Okay, so in both respective. Somebody's going to be gaining and somebody's going to be losing, right? So if we sit there and say that, energy is going to be basically conserved. So we can say Q is going to equal, let's say, the system is going to equal Q minus Q of the reaction. Okay? Because one is gaining, one is going to be losing. And there, in terms of heat, right, we're saying under special circumstances, we're going to say that one is giving up and one is taking, and they should be equal to each other, right? You guys have that look on your faces. What does that mean? I should say Cassie has that look on her faces. Everybody else has black screen, so.
I was gonna say I'm the one that you could see.
So, but you speak for everybody because it's just me and you because they don't show their face, so they don't count, right?
Well, I was just trying to process what you were saying, but I mean, it makes sense.
Yeah. Okay, because one is going to be gaining that energy, and one is going to be losing it. So that means that value for Q, one is going to have, if it's gaining it, it's going to have a positive value,
And
and then one that's going to be losing it is going to have a negative value, right? Make sense?
Yeah.
Okay, good. Okay, so let's use this equation. So we're just going to use it very generally, right? So if we want to just determine, let's say, in a flask, let me get to the question. In a flask containing 0.8 times 10 to the second grams of water is heated, and the temperature of the water increases from 21 to 85 degrees Celsius. How much heat did the water absorb? So what am I going to do in this situation? How am I going to be able to calculate the heat?
You plug and chug with your Q equals C.
Which one am I going to use? Q equals capital C?
No.
Delta T? Or am I going to use Q equals M little c delta T?
Yes. The second one.
Okay, so we're going to be using this one.
Yeah.
Okay, so Q equals, what is M? Oh, Mauricio, what is M?
M would be the mass of the water, so 8.0 times 10 raised to the power of 2.
Okay. Okay, let's see. Maddie, what is C?
I don't know because I'm looking and I know that the delta T would be the change from the degree Celsius, but
Okay. So we'll put delta T is equal to, so what would delta T be equal to?
that would be 64.
Okay, so it's T final minus T initial.
Yeah, and that's 64. It increased.
So that's 85 minus 21 degrees C. And so you get 64. Okay, somebody want to tell me what C is? Lowercase c, what does that stand for again?
That's the
Calorie.
calories.
So that one changes the degree by 1.
Oh, that's your where you would put your joules.
Each
That's
is your
right.
given.
So,
Okay.
Joules, or however you say it.
yep, joules per gram. So that's our specific heat, right? Per
Okay.
gram degrees Celsius.
I was
So
looking
is
at
that
the equation.
so is that just dependent on like what you're dealing with?
That's right. Since we're dealing with
Okay.
water, we know it's going to be 4.184 joules
Right.
per degrees. I mean, joules per grams degrees Celsius.
So you would need to use your chart
Yep, that
depending
table.
upon what it's given. Okay.
That's right. So we could have been talking about steel, right? Or
Right.
iron. Is an iron on there?
And so, okay, so it's specific heat for that particular compound.
That's right.
Okay.
Yep. Okay. So we get Q is equal to what? Let's see. Who's going to do the math? Stefano.
Trying. Ooh.
Yeah.
You going to do the math for me?
Oh, let me get a calculator.
Dr. Henry,
Yes, ma'am.
is this one of the equations where if you don't put the parentheses in the right place, you'll get your answer wrong?
Yes, you could get your answer wrong if you don't put your parentheses in the right place. Yeah.
Okay.
How many sig figs are we going to have starting out, Stefano?
2.
2? Okay, so I get, this is what I get, times 10 to the 5 joules.
I got a very long number, but with the 2 sig figs, it's the 2.1.
Yep. Piece of cake, simple.
Yeah.
Mm-hmm.
Okay, good, good. Okay, let's see if we can make it a little bit harder.
I knew that was coming.
Okay, so let's say we had, let's talk a little bit more first. Okay, so we are using thermochemistry throughout various sectors. One of the major sectors that are currently, that's a really hot sector right now, is solar panels. Now, if you think about your solar panel, so right here, you have your panels that are actually collecting heat. So they're actually just heating up a liquid or a fluid. So that steam, or in this case, it's going to be steam, or it could be some other form of liquid, a coolant. And so sun's beating down, the solar panels is collecting all that heat. That steam is then being used to turn the turbine, and then the turbine turns the generator, and that's going to create your electricity, right? So then the steam then goes up, gets cool, and then gets reheated. And so this is an endless cycle. So this is one way of looking at the heat that's being transferred from the sun to the liquid that's being stored in that solar panel. Okay.
I have a question.
Yep.
So just by what you're talking about, in the winter time, wouldn't you have a decrease in energy production because it's colder, so it's not going to heat up as efficiently? Well, not efficiently, but
no, that's definitely true. Yeah.
Okay.
So in certain times during the day, particularly here, because here, if you're getting at least 70 degrees of temperature. And that's the reason why it's not always water that's being used. Sometimes it's other coolants, because then they're able to produce that steam that allows that turbine to use. So stuff that would have a lower boiling point
Okay.
often will be used in these as well too. And it's more commonly used now because it makes it a little more efficient, right? Don't take much to sit there and get a lot of steam produced in that situation.
Okay.
Yeah, but you're right, in the winter. So in cold places like Ohio and stuff, you don't see a lot of solar panels. You see a lot of wind, the wind generators,
Yeah.
the windmills. Okay, calorimetry. Calorimetry is basically just the study of it's how to measure heat that's being transferred. You guys actually made a kilometer this weekend, right? It was a fancy one too. You have that look again, Cassie. Your face tells everything. You're supposed to help me with my lie here. For anybody who didn't show up, right?
Don't put me on the stand because my face will give it away.
I see that. I see that. Okay, so
Sorry.
So you guys actually built a kilometer this weekend, right? And so it was real simple. You had a probe, a cup with a lid, right? Pretty simple. And so the way that actually worked was you guys were just measuring the environment that a reaction was taking place. Straightforward, simple, right?
Mm-hmm.
Okay, so calorimetry is, again, it's used to measure the amount of heat that's being transferred from one substance to another, or the amount of heat that's being transferred from a reaction. And you guys did the heat of neutralization. Is that correct? Okay, so it wasn't too hard. So this is like in that ballpark, so you should be able to do that whole lab, right? Without a problem. Okay, so when we talk about, as I told you, we have our system and our surroundings. Okay, so our system is going to be the substance that's going that physical change or that heat, and our surroundings is what's going to be kind of absorbing that heat, or that is going to be providing that heat, one or the other. Okay, so if we had a cube of metal, a hot piece of metal, and we drop it in a tank of water, what is your system and what is your surrounding?
Piece of metal is the system, right?
Okay.
And the water's the surroundings.
And the water is the surroundings. Okay, so the metal, what's going to happen to the metal? Is it going to be a hot piece of metal? Is it going to be releasing heat, or is it going to be absorbing heat? Is it going to be endothermic, or is it going to be exothermic? As we drop that piece of metal in water,
Would it be exo?
it is going to be exothermic. That is correct. Okay, but okay, so the water is going to be then
Endo.
okay. Okay, simple, right? Yeah, no, maybe.
Wouldn't the thermometer be absorbing in order to measure?
Yes, the thermometer is also absorbing some of it to measure it as well. So, yep.
Oh, never mind. I see it. Okay, I see it. Just kidding.
Okay, so here, if you take a look at it, it actually shows you the heat going out into the water, right? So our surroundings is absorbing the heat. Okay, so if the surrounding is absorbing the heat, so what would you expect from the surroundings? So what's going to happen at the end of the reaction?
Surroundings are going to be warmer.
And then what's going to happen to the metal?
It's going to be cooler.
Okay.
So wouldn't that be like thermal equilibrium then?
That is correct. You're going to get thermal equilibrium. And that's part of the reason why we could say if there's no work being done on the system, let's say, for instance, the metal is below 100 degrees Celsius, right? Or we know that no work will be done on the system because you're not producing any gas or anything like that. You're just changing the temperatures. So in that situation, we can sit there and say Q is going to equal Q metal is going to equal minus Q water. Okay. Are you with me?
Yep.
Okay.
Yep.
So that also allows us to let us know that there's going to be equilibrium, right? Because if we define Q metal, so we say Q metal is going to be equal to, what is that equation?
Was it the small or big?
Small, right?
So C or MC delta T.
Okay. M small c delta T.
So how do you know when it's the larger calorie?
It's not larger calorie, it's the larger capacity. Remember, one is called heat capacity and one is called specific heat.
Oh, specific heat. Okay.
Yeah, specific heat is the small c
Yeah.
because it's so damn specific. And then heat capacity is the big C, right? And so usually in the problem, it'll say heat capacity.
Okay. And
blah,
then
blah,
specific
blah.
heat.
Yeah, and they'll give you
Okay.
a value, right? Because one is dependent on
Mass.
And so the one that has mass in it isn't dependent on mass because you have to add it in there because it's independent of mass.
Okay.
Okay.
Never mind. Okay.
Okay, let's see. So, and then we're going to say that that's going to equal minus. Oops. I'll do it like this. And we know that Q water is going to equal M C. And so that would be C of the metal. And then this would be C of water. Delta T of the metal. Okay, so let me throw up a problem. Okay, so what are we going to do? So if I said if 95 degrees, if it, let me fix this. If an iron cube at 95 degrees Celsius weighing 10 grams is dropped into 10 degree Celsius of water weighing 50 grams, what would be the equilibrium temperature? So how would I solve that?
Would you have to use the one with the small c? Yeah.
Yep, we're going to use the one with the small c. That is correct. So where would I get my small c's from?
From that chart.
Okay, so let's go back to the chart.
Maybe you're using iron and water, right?
Iron and water.
So water is the 4.1.
Goes small c water. That's a W, really. Equals 4.184 joules per gram Celsius. And small c iron is equal to what?
0.449.
Joules. I don't know why I made that 9. The curve. Joules per degree. Grams. Okay, so what are we going to do now? So we've established we're using this equation, right? So what do we know about delta T?
You're at 95 and 10.
Am I at 95 and 10?
What would be
So
the
delta
difference?
T, what was that?
It'd be the difference.
Would it be the difference between 95 and 10? What's at 95 degrees?
The cube.
The cube is at 95 degrees. Okay.
And the water is 10.
Okay. So you're telling me.
Oh, okay.
Okay, so what do we know about the temperature at the end? What's going to happen? If we let it sit long enough, what's going to happen?
You're going to get a balance.
You're going to get equilibrium, right? So your initial temperature, Ti metal, is going to be 95 degrees Celsius, right? Ti final is going to equal our equilibrium temperature, which we don't know. Or say Ti final for the metal. Now, what about the water?
It's 10
So
initial.
Ti water initial is going to be 10 degrees. And then Ti final of the water is going to equal our T equilibrium. Okay, so if we go ahead and put these into our equations, right? So we say Qm equals minus Qw. This is what Qm and Qw are. So it's 10 grams times the specific heat of our metal, which is 0.449 joules per gram degrees Celsius times so T final which is TEQ minus 95 degrees. So we get 0. .449 joules Celsius TE minus then this guy down here is going to be 50 grams times 4.184 joules grams Celsius times. So our T final is going to be TEQ minus 10 degrees Celsius oops,
Dr. Henry, on your medal, it's 4.49 grams per
Yep.
the second half. The second half. Minus 426.5 grams
Yep, it's
over
4.49 joules per degree Celsius times TE
and then the second half minus
minus 426.55 joules.
joules.
Yep. Minus 2,092 joules. Okay, so if we set these two equations equal to each other, we get 4.49 joules degrees Celsius TE minus 426.55 joules equals negative 209.2 joules degrees Celsius TE minus 292 joules. So then we ended up with so we end up with 2 518.55 joules. Plus 213.69 joules per degree Celsius, TE. And if we solve for TE, we get TE equals 215. One. 215. 8.55 joules divided by 213.69, and that would be degrees C or joules. So you get 215, 213 point. $11.8 degrees Celsius. Piece of cake, just long.
Kinda, yeah. I'll get it.
See it.
It's just long.
Yeah.
Too long.
Is that 218? I'm having a really hard time reading that, Dr. Henry.
Where?
So the TE equals 2518.55.
Yeah.
Okay, divided by 213.69.
Divided by 213.69. Yeah.
Okay, sorry, I'm blind.
That's right. And obviously, I didn't use sig figs because otherwise, if we use sig figs, I just gotten a really crazy number. I got 10, essentially. Okay, questions, concerns, cash, credit, Warbucks. Okay, so that's going to be it for today. There's not going to be a lab.